So our next speaker is Professor David Dunson. He's an arts and science professor at Duke University, and his title is Scalable Bayes, Simple Algorithm with Guarantees. Thanks a lot.
Thanks for the invitation. So we'll have the same talk over again, I guess, but in some sense. So I'm going to talk about Scalable Bayes, and I'm going to be looking at a very similar type of problems to what Ryan was talking about, but from a quite different perspective. And in particular, we're not trying to define Markov chains that are converging to exactly the right stationary distribution corresponding to the posterior distribution, but I'm trying to put in approximations. And then having guarantees on those approximate classes of algorithms. So it's a little bit different game, quite different game. And I'd say that's really worth doing because if you run an MCMC algorithm, if you ever do this in practice, saying that we need to be converging to exactly the right stationary distribution, and then we get these super noisy autocorrelated samples, and then get this like enormous Monte Carlo error, maybe that's not the right trade-off between this issues of kind of statistical precision and noise or uncertainty. Okay, so I'll keep the background on Scalable Bayes very limited because Ryan did a great job with that. But basically we have two ideas which you can't see here. Are the first I call WASP because we wanted to come up with some sort of animal that could beat up on fireflies. And then the second class of algorithms is just Approximate MCMC. Okay, so we want to be able to deal with not just big N in general, but also big P type problems. And so I work a lot on scientific applications involving biomedical data where we have very high dimensional data, and the sample size isn't necessarily that huge. But today I'll talk about initially how do we deal with the big P problem, and then can we use these kind of types of approximate MCMC algorithms maybe in combination with the first class of algorithms to deal with larger P type problems. Okay, and so the really speed and generality and ease of the algorithms is really important. And so I'd like to have something that's incredibly general. And so you could imagine something like a probabilistic programming language like Stan. And then, okay, well now I'm trying to run a Bayesian model. It could be almost any Bayesian model in Stan and get samples out and get posterior summaries. But my data are too big and it drags to a halt. And so I'd like to be able to just have a simple add-on. Take any sampling algorithm, it could be MCMC, it could be SMC, it could be anything, and just have some simple modification to it that I can put in some sort of automated package and then easily be able to do that in general. And then I'd like the algorithm also to be simple and transparent so that if I was coding it or my grad student's coding it or even some applied researcher is looking at an algorithm and they want just a simple fix-up for the size of the problem that they can do that. Okay. Another point is that I think big data in general as a field has been dominated by people who are doing sort of optimization type problems and getting point estimates, I think. And so that it's really definitely the case even in big N problems that I've seen that characterizing uncertainty well is really crucial. And just even using like large sample Gaussianity assumptions doesn't really cut it. Often in big data we're interested in more complicated models, we might be interested in rare events, et cetera. Okay, and so Bayesian methods are really nice, I think, in this domain for allowing you an approach for modeling the complexity of massive data. It makes you also more creative, I think, and compared to doing penalized optimization type approaches where, you have some loss function, you put a penalty down. It doesn't give you enough structure into the problem, and then people will think a lot about designing structured penalties and things. But I think the modeling paradigm is more natural often. Okay, and so I'll put up my Bayes posterior here, but so essentially, so we're interested in this full data posterior distribution, and we'd like to approximate this, but not really approximate the whole thing. Usually, theta is some parameter that could be pretty high dimensional, and we might be interested in some sort of posterior summaries of some low dimensional functionals or even one-dimensional functional of that theta. And in general, if we're doing MCMC or sampling methods, we have this posterior distribution. It's proportional to the prior times the likelihood. We have this intractable normalizing constant, which is the marginal likelihood. And that's why we're running some sort of sampling algorithm. And then those samples will converge to a stationary distribution that corresponds to the exact posterior distribution. But we can't really run it practically in practice in big problems. Okay, and so that's because the sample size is large and also the size of the parameters is large, and so that integral in the denominator is intractable. And there's been a lot of really interesting work trying to come up with analytic approximations, like variational Bayes is a very successful approach in the machine learning literature. We've actually found it actually works surprisingly well in trying to compare it to a number of our algorithms. I was actually quite shocked at how well it did in certain settings. But in general, I'd say it's definitely true that accurately, analytically approximating the posterior, and particularly this normalizing constant in the denominator, is super nasty. You have a high-dimensional integral, some arbitrarily complicated model. It's really hard to come up with general algorithms for that, approximating that denominator. And that's one of the real reasons these sampling algorithms that try to bypass that calculation have been so successful. And so that's really why I think Markov chain Monte Carlo and related algorithms like sequential Monte Carlo sort of remain the standard in the general literature applying Bayesian methods. Okay, so we'd like to scale up these algorithms. And so I'll sort of skip these existing big data algorithms. Ryan did a really nice job, and I really couldn't do them justice anyway. But the general game people try to play is often you might not want to look at all the data on one computer, so we might like to split up the data on many different computers, or not do computations for all the data at once. And Mike Jordan had this really cool approach, for example, which is called a little bag of bootstraps or something, where you would sample a subset of the data and then do that many times and then combine. Okay, and so there's a lot of approaches like that, or also a lot of online approaches using stochastic gradient descent is very popular. In the Bayesian case, as Ryan put up a slide sort of summarizing these scalable MCMC methods, and so there's two main camps in that setting, and the one is to try to divide up the data into blocks and throw it on different computers and do things in parallel and then sort of combine, ideally with minimal communication across the different computers, and the other game is to sort of look at subsets of the data as you go on, and Ryan had this really cool idea to avoid this sort of approximation in that, but most of the methods out there are basically trying to sort of mix stochastic gradient descent and sampling. Okay, and so the algorithms I'm going to propose, the first one is called WASP, and the second one, depending on time, I might not go into as many details, is Approximate MCMC, which is really an existing algorithm that we just put under an umbrella for theoretic study. Okay, so Wasserstein posteriors, that's the first part of my talk, and feel free to interrupt me at any point. Okay, so what's the big idea here? So the basic idea is super simple, and many people have done the same type of thing already. We just do it in a little bit different way. And so we have some big data set. We have some huge data set, large sample size. We could also have a reasonably pretty big dimension of the data as well. And so we don't want to put all the data on one machine. And so we break the data into subsets, okay? And then based on those subsets, we're going to get what we call subset posterior distributions that we then want to combine. And we want this combining step. We'd like to be able to do this in an embarrassingly parallel way, just completely separately, really simple way, just a simple modification to existing sampling algorithms to get samples from these subset posteriors. And then we want to combine them really, really quickly, minimizing communication costs really fast. And we want that combined thing to have really strong theoretic guarantees, which is lacking from existing approaches. Okay? And so here's an example. I put up my logistic regression to match Ryan's lead here. So we have a toy logistic regression example. And so what I've shown here is what we're doing. So we break up the data into different subsets. We adjust the subset posteriors. We run sampling for each subset posterior, and then we just, in this case, I'm just showing the contour plots for two parameters, the marginal posterior for two of the parameters. And each of these green here is a different subset posterior that was calculated just completely separately on a different computer. The MCMC, based on putting all the data on one computer, running MCMC for a long time, the contour plots are shown in blue, and the contour plots for our approach is shown in red. And we can show that they're actually going to do a really good job in general at approximating this posterior distribution. Okay. And so the thought here is that from the subsets, each subset posterior, we have a noisy approximation of the full data posterior. And so we have all these noisy approximations. And so if we could think of these guys as sort of like points in some sort of metric space corresponding to a space of probability measures, and take some appropriate mean in that space, and we could calculate that really fast, then we get a probability measure, which is this central probability measure, and that's what actually we were doing. Okay. Okay, so WASP. So what are the underlying assumptions? And so we have two main assumptions. The first is that the posterior distribution has finite second moments. And this only has to be true for the things we're interested in inferences on. Because you could imagine we might have a model with many, many parameters. And we're running MCMC, say, separately on all these different computers. And we might have 10,000 parameters in the model. But we might only be interested in 5 parameters. And so those 5 parameters that we're interested in, that's what we're going to be doing the combining for. Those have to have finite second moments. Also, the parameter space has to be a metric space. And so that's very, very, very broad. And so we can't have some sort of weird model where the parameter space is not a metric space. OK, so the pieces that we're putting together, so we're going to use stochastic approximation for each subset posterior, because we need the subset posteriors to have the appropriate measure of uncertainty as if the same as for the full data posterior. Because when we take this average in this appropriate space of probability measures, it's not going to make them more concentrated across the different subsets. And so we want to use stochastic approximation to sort of adjust. What we do is essentially we have a subset, we replicate the data on the subset up to the full data sample size, and we put that in Bayes' rule to get the subset posterior. And so that's the stochastic approximation step. And I'll show the details. OK, and then we combine those subset posteriors through their Barycenter in the Wasserstein space of order 2. And so we're just essentially taking an appropriate mean of probability measures. And the cool thing is that this can be done really, really fast using just a linear program. And so the time taken to combine is very negligible compared to sampling for each subset. And so we can scale to really bloody enormous problems. If we have enough computers, there's essentially no extra time for blowing up the sample size. And we also have shown recently, I won't put it in this talk, but you can even just take a quantile for a one-dimensional functional for each subset, and you just average them. That's all you have to do in the combining step. And we have very strong theory showing that those averages will give you very good estimate of the average for the Wasserstein posterior, giving you a good estimate for the quantile for the true posterior. OK, so let's go into the details a little bit. And so the full data posterior, which we can't get a really good handle on, is like this. OK, so that's a product from I equals 1 to n. And so we're going to look at, we have likelihood, we are limited to likelihoods that have this type of product form. But this is really quite general. You can imagine that you have a product from I equals 1 to n. We can actually deal with hierarchical data sets or time series or spatially correlated data sets as long as we have some sort of conditional independence structure given random effects. Okay. And then we divide the full data into k subsets of size m. And we could use unequally sized subsets. And we could even do sort of like bootstrap subsets. But for theoretical purposes, we're assuming that we take the full data set, sample size and we break it into non-overlapping subsets. And just for simplicity, we can think of them as being equal sized, all of size m. OK, now we get a subset posterior density for the J subset. And so that's just like applying the same thing, but now we're just taking all those subjects in a subset. Okay, and that'll be relatively small. Those are all the data sitting on one computer. And then we do this adjustment to the likelihood. We don't just take the subset posterior, but we raise it to a power gamma n, and that's where the stochastic approximation comes in. So in general, if we can think that, well, if gamma n, if that was just k, as it would be in simple cases, then all we're doing is essentially taking the data in the subset and replicating it up to the size of the full data so that the posterior distribution is essentially a noisy approximation of the full data posterior distribution. OK, and so now we have these subset posteriors. What the hell do we do with them? So we're going to take a Barycenter in the space of probability measures. And so it's just essentially a fancy mean. And so we have some space that's no longer a simple Euclidean space, but a space of probability measures. And we're going to use a Wasserstein 2 space. Each of the points in this we have thrown down in this space are different subset posteriors. And we want to just, we need a metric characterizing the distance between a given point and each of those subset posteriors. I call that rho, and we'll use a Wasserstein 2 metric. And then now we just calculate the Wasserstein Barycenter is just going to be the sum over all those different points. of the distance between some central point and each of the subsets. And we find the central point that minimizes those sum of squared distances. And that'll be a type of mean, or Barycenter. Okay, and so, yeah.
Weighted by the size of the subsets?
If you had different subset sizes, you could put in weights there. So the general form, you would have some weighted mean. But we're in general thinking equally sized subsets, and then you can just use the same weights in all the examples I've shown. But the general procedure allows for arbitrary weights on the different subsets. Okay, and please interrupt me if there's any questions as we go on. So. Okay, so we have a Wasserstein 2 distance. I don't have time to go into it, but Wasserstein is a really nice distance that people haven't used that much in statistics and asymptotics, but they use a lot more in mathematics, which is essentially an earth mover's distance. And so we could think, if we have an atomic approximation to a posterior that we get from sampling from the parameters of the posterior, we have all these atoms, and then now we have another atomic approximation. It's like, well, now we have 2 piles of sand, and how much are we paying to move the sand? We move the atoms and move the weights on each of the atoms to the other, and that gives you the Wasserstein distance, also known as the earth mover distance. And so it's a very nice geometric distance. Other distances, particularly in the atomic case, can sometimes give you strange results. Okay, and so now we simply combine these different subset posteriors using their Wasserstein Barycenter, and this is what we call the WASP, or it's for Wasserstein posterior. Okay, and so that then if we had this guy, if the subset posteriors were just in their initial mathematical form, this would be completely intractable to solve that. But we have samples from each of these subset posteriors, and so then we have an atomic, discrete approximation of the subset posteriors. And so if we put that in, that's where we can just use a fast linear program to solve, to calculate this pi bar, okay? And even if we're interested in one-dimensional functionals, we don't even have to do that. We can just average the quantiles. Okay, so that's the point there. So some theory, and then I'll show some examples. So there's this very general theory that has been sort of pioneered by Subasis Gosal and Odd van der Vaart, proposing frequentist properties of Bayesian posterior distributions, including in non-parametric and nasty cases. And so in this 2007 paper, they proposed a sort of general posterior concentration rate theorem. And so we wanted to see, well, could we have some corresponding theorem that looks like that, but not for the true posterior, for our Wasserstein posterior, okay? And so we wanted a similar, very general, broad theorem. But we found when we started playing with this that it wasn't actually very easy. And we had a machine learning paper on this WASP stuff over a year ago, and it took us that entire time to kind of write a statistics paper because we're working out all of these details. And two of the non-trivial details are that really what people have been playing with in the statistics literature on posterior concentration rates is based on Hellinger distances. And here we need to work with the Wasserstein distance, which is annoyingly unbounded. And the sort of math details don't fall out nicely. The other thing that we ran into is we had this stochastic approximation in the likelihood. And there was a really, really cool result by Stephen Walker showing that you could actually take the usual posterior distribution, take the likelihood, and then raise it to a power that was less than 1, and you could actually get a posterior convergence rate theorems that had less restrictive assumptions on the prior. And so that made things easier. You were sort of upweighting the role of the prior, in some sense, relative to the likelihood by raising to a fractional power. But we're doing the opposite, and so things sort of get nastier in some sense. Okay, and so the sort of bottom line is that we could deal with this first problem by lower bounding the Hellinger metric. And so then we introduced this alpha parameter, which is controlling the regularity of the model under consideration. And then we played with extending the previous literature on stochastic approximation to deal with the other problem. Okay, so our main theorem, our first main theorem, what is this? Ugly mess. So what we're doing, which is different than in existing theorems, is we have some parameter space big theta. Let's say the true value of the parameter is theta naught, which generated the data. And so we're taking an expectation under the true data generating model. and now we're putting a point mass at the true value of theta, and we would like the posterior to concentrate around that. So we have a point measure at that theta naught. We'd like the posterior to concentrate around that, ideally fast, okay? And so we're putting a ball on the expected probability, or the expected Wasserstein distance, okay, between the Wasserstein posterior for this is just for the subset posterior, then we'll show the Wasserstein result, and this point mass. And so we can see that it's bounded by a constant, which is independent, just a arbitrary constant. And then we have this log 2m, a log factor, over m raised to the 1 over alpha. And m is the subset sample size, and alpha is the sort of regularity of the model. So if we have a regular parametric model, then alpha is going to be 1, and then we're going to get a parametric rate of concentration of the subset posterior up to a log factor, which is nice, even with the stochastic approximation. Okay, and so we have two extra conditions over the usual posterior consistency convergence rate theorems, and one is that Hellinger one, and another is also based on the distance. Okay, I won't go into the details about this one. This one will depend on the model you have, because that sort of verifying this condition will give you an alpha value, which will be impacting the rate of convergence. Okay, and so now we need to put in together all these subset posteriors into the Wasserstein posterior and see how that converges, and we get a corresponding convergence rate theorem on the Wasserstein posterior, which now is the square root of a log factor divided by km to the 1 over alpha. So if alpha is a regular parametric model, alpha is equal to 1, and then km is just the total sample size. And so we're going to get a parametric convergence rate in a regular parametric model up to a log factor for the Wasserstein posterior around the true value of the parameter. And we also get that for functionals. So, enough on the theory. Let's show some examples. So I wanted to give a couple of representative simulations that illustrate some of the applications. It's incredibly general, and it's incredibly easy to modify existing sampling algorithms to deal with this trick. So just as an example, we show a logistic mixed effects model where we have repeated observations nested within subjects, and also had a mixture model, which is a type of probabilistic tensor factorization for high-dimensional tables. Okay? In both of these cases, it's easy to write down a Gibbs sampler. There's existing nice sampling algorithms. We can just modify them just very, very slightly, run the sampling algorithm for each subset, and then combine trivially. Okay? We also applied it to the movie lens data because that's a sort of canonical big data example. Okay, so here's the mixed effects model, and so now we have subjects I equals 1 to n, and now we have repeated observations within each subject, and we have a logistic mixed effects model. We put down just Gaussian random effects and usual type priors, and we have there's a nice MCMC algorithm based on Polya gamma sampling. Nick Polson and collaborators came up with this really beautiful data augmentation algorithm. I agree with Ryan about data augmentation algorithms being cool, and this Polya gamma sampler works really well. But the problem is that we're sampling latent variables for every observation. The number of observations gets big, that becomes very, very slow. Okay? And so here we can just do it separately for subsets of the data on each computer and then combine the results. And so we can scale up arbitrarily faster. Okay, so here's some of the results just for the fixed effects. So in this case, we had the sample size was 10 to the 5th, and then we had just 20 subsets, and then we had 10 to the 6th sample size, and we had 50 subsets. And we didn't want to make the sample size too big because we wanted to run it versus just vanilla MCMC. Okay? And so the first column we call BVM because we just rely on the Bernstein-von Mises theorem to give a large sample normal approximation. That actually works surprisingly well, and it's sort of underappreciated that, well, if you have big data relative to the number of parameters, then it's probably the posterior is asymptotically normal, and you can maybe just use a normal approximation. Okay, and so then we also compared with MCMC. We tried to develop a sort of state-of-the-art variational Bayes algorithm. There's an existing algorithms out there. And then we had our WASP approach. And you can see that what happened in general, as we get up over here, for example, and the variance components is a more interesting case, is that we saw that usually what happens in these kind of more complicated hierarchical data cases is the variational posterior is sort of on in this case, but it has slightly too low variance, whereas the WASP actually looks like it has slightly inflated variance. Like maybe those log factors are an artifact of our theory, but maybe actually the WASP posterior is slightly inflated variance, which I actually think is a super good property, because I often think that one of the problems with Bayesian approaches and big data is that they kind of tend to underestimate uncertainty, if anything. Okay, and so again, for the variance components, you can see that in the larger sample size, all the approaches were essentially dead on. Okay, and so what about the time comparisons? We want to be a lot faster. So this is log of the time. And MCMC is bloody slow, becomes even more slow as the sample size goes up. And WASP is essentially arbitrarily fast, because as long as we have enough computers at our disposal, we can combine in trivial time, and so we can just throw it on more and more computers and not bog down with bigger data sets. We can also do it for complicated models, like this is a non-parametric Bayes model for contingency tables. We have a Dirichlet process. We have had previously developed these types of models. It can automatically learn the rank of a low-rank tensor factorization. And we have a nice Gibbs sampler, data augmentation Gibbs sampler, to implement this model, but it becomes pretty slow, because what are we doing in mixture models? You're allocating each observation to a different mixture component, and so you have to scan through all of the data, and so that becomes very slow. But we can just throw it on different computers. We can scan through all the data for each subblock in parallel, and it becomes much, much faster. In this case, I'm sure we could work out the details in a variational Bayes algorithm. That's one of the things about variational Bayes. There's now some ways to automate that Dave Bly and other people have worked on, but in general, you have to kind of work out all the details. This we can sort of apply in general using black box MCMC or existing MCMC algorithms. And so we compared in a simulation study to MCMC run for a week and a day, and we saw that for every parameter we got essentially just absolutely dead on the MC results and supermassively faster. But if you looked at really closely, you can see you're dead on, but maybe the variance is just tiny, a little higher, just a little bit higher. Okay. We also did it in a movie lens. It was the same kind of story. VB in this case was a little faster. If we had more computers, we could make WASP faster. Of course, you can parallelize VB as well. Okay, so we could do Gaussian process regression. Our theorems I showed before do not hold in the Gaussian process case, but we're working on that, and we're quite optimistic about having some general non-parametric theorems, including Gaussian process cases. But what's really cool about this is that the literature on Gaussian process computation in big data now essentially always makes low-rank approximations, and so we don't have to make any low-rank approximations. We could just break the data into subsets, run in parallel and combine, and in this simulation, other cases, it looks like we get extremely good results. Okay, so just a summary, the first part of the talk on WASP, it's really a simple modification of existing MCMC algorithms for big data. You have 3 steps. You randomly partition the data into smaller subsets. Here we've just been doing that in simple ways. If we have more involved, complicated settings, it's a sort of open area for how to sort of efficiently and optimally do that partitioning. We get posterior samples after stochastic approximation across every subset, and then we really fast find the Barycenter. Or if we're interested in one-dimensional quantiles and one-dimensional functionals, we can just take an average. So in the future, you can actually do this on Stan. Stan has an option for putting in weights on the likelihood, powers on the likelihood, and so you can sort of trivially do this already in Stan. And so it would be nice to actually put that into Stan. We'd like to get better theory. It's quite interesting. We just got an NSF Big Data Foundation's large grant funded to kind of focus on these things more, and so it's going to be a lot of fun working with actually mathematicians on trying to work out the details and come up with really general classes of algorithms. Okay, the other thing I'd like to talk about is Approximate MCMC, because one thing we found, is that, well, we have this approach. Most people, they're trying to deal with the big N problem, But in practice, there's all these people who are using MCMC algorithms all the time, and they have big and complicated data. And what they do is they often don't stick to the MCMC rules. They'll use some approximations. Like I'm doing a Gaussian process, MCMC. What do people do all the time? Well, I'm going to do a low rank approximation here. Maybe down here I'll use a normal approximation or a grid approximation, and I'll just run it. But then I never talk about like what the behavior of that MCMC algorithm is. And so we'd like to be able to like take an MCMC algorithm and put in approximation steps and then have some theoretic guarantees that say, well, this thing still converges to within some small neighborhood of the target. Okay. And so it's a different way to speed up MCMC. We can use it in combination with WASP, actually. For each subset, we could be using approximate MCMC. Okay, so I gave those examples. We might approximate a conditional distribution in Gibbs with a Gaussian using a subset of the data. We might use a low-rank approximation. There's lots of examples already in the literature. So this potentially can vastly speed up MCMC sampling. Okay, so we know that, hopefully anyway, under some regularity conditions, that the original MCMC sampler converges to a stationary distribution corresponding to the exact posterior. And Ryan had these like really clever algorithms for making that true also in the big data case. Okay? But what if we use approximations? We start putting in approximations to these MCMC transition kernels. Who knows what will happen? It might diverge. It might get worse with iterations. It might converge to something that's arbitrarily far from what we're interested in. And so that's not good. So there's been, until recently, almost nothing on this, but in the last couple years, people have gotten really interested in this. It's kind of a hard problem. And one of the real leaders in this area is actually in the Nitesh Pillai in the Harvard Stat Department here is really doing outstanding work with a really talented student of his in this area. And what he's been looking at is more focused on what happens when you have subsets of data, but I think the tools there are really generalizable. There's also another paper that looked a lot like the Nitesh's paper, sort of in parallel, that was playing a related game that was just posted to arXiv. And so the usual focus here is like what happens when you approximate based on conditioning on subsets. And so the sort of question of, well, okay, I have some general AMCMC algorithm. I'm not necessarily conditioning on subset. And I'd like to take into account the fact that I'm doing statistics here. I'd like to use these samples, and I have a particular loss function, and I'd like to come up with Monte Carlo estimates of something, okay? So can we take that into account in assessing the theory and really use the theory as a lens for saying, this algorithm doesn't look very good. Maybe thinking of this theory, we can actually design new algorithms. Okay. There's another paper, but. Okay, so we'd like to focus on estimation error, interpretation of the error bounds. And I sort of said these things already. So let's like kind of get to the meat of it and then finish up. Okay, so we have two conditions. We wanted to be very general, but have something that would result in simple interpretable bounds. Because really we want to be using this theory as a sort of a lens to kind of decide between algorithms in a sense. And so we wanted to keep the theory simple, and for that reason, we kind of made the two conditions reasonably strong. But we can verify them for really interesting models. Okay, so for the first assumption, we have this type of Dublin condition on the exact chain. And so that would be, this is for the exact, we're approximating some Markov chain Monte Carlo method, so we have an exact transition kernel, which will converge to the exact thing. Maybe we've used Firefly for that or something. Okay, and so now we say, well, there exists a constant alpha such that the supremum over all pairs theta, theta star of the total variation distance between the difference in transition kernels is less than 1 minus alpha. Okay, and so if you have a compact parameter space, which arguably you can compactify most problems from the standpoint of applications, then this is not so difficult to show. It can certainly be relaxed to divide the parameter space into a bad and good region, and then have some small probability bounds allocated to the bad region, but that sort of complicates our story, and so we won't do that here. It's similar to uniform ergodicity. Okay. So the other type of assumption we need to make is not on the exact chain, but the level of approximation. Okay. And so we have an initial exact transition kernels, P of theta, that's our exact transition kernel. And we'd like to approximate that. And so we have a family of approximate kernels, P, and we were going to put this type of condition on the approximate kernel. So we're going to say there exists a constant epsilon, which bad things happen if epsilon's bigger than alpha over 2, such that the supremum of all theta in the parameter space of the distance between the transition kernel starting at theta and the approximate transition kernel starting at theta, that in total variation distance is bounded by epsilon. Okay, so this is a sort of uniform bound in total variation distance between the exact and approximating kernel. We found actually in quite a few models we could show these two conditions, or something very close to these two conditions. Okay. And it again can be weakened to hold in a high probability subset. Okay, so here's our main theorem, and so it should be obvious from this what we're talking about. So I tried to limit it somewhat, but just focus on the top part, okay? And so we're going to assume those two assumptions. The assumptions, we have this doubling condition on the exact kernel we're approximating, and we have this uniform total variation bound and epsilon on the approximate kernel. Okay, so under those assumptions, let's say we want to estimate, that's what we usually want to estimate some functional. That's what Ryan was saying, some posterior mean or something, posterior expectation of some functional. So the true posterior expectation of some bounded functional f is pi f. Okay, so we'd like to approximate that. So it makes sense to say, well, let's look at the expectation of the distance between the Monte Carlo estimate of that and the truth. Okay, let's look at that squared, the expectation of that, and we'd like to bound that. Okay, and so if we're using the exact MCMC algorithm, we would have this bound. Okay, and it can be weakened to not have a bounded f, but don't worry about that so much. And so what do we have in this bound? Well, t is the number of iterations of the Markov chain. Okay, and so that's going to be dropping off, this part. It's going to be dropping off, and sort of how fast it's dropping off depends on alpha. Okay? And so now we come in, we put an approximation in instead, and so this is what the bound for the exact. So if we put an approximation in instead, now we're using samples from the approximate chain, but now we have a slightly different bound. And so what do we have in here? We have everything's the same except for epsilon squared over 4, okay, which is a bias term. And so we're throwing in a bias when we use the approximation. And so what we would hope is that, okay, if we use an approximation, we get some speed up per iteration, S epsilon, and then we have a computational trade-off. We have a speed up per iteration, and we have some asymptotic bias. Okay, and it's the same story down here, but we're looking at concentration inequalities. Okay, so the implications are if the approximate chain has speed up S of epsilon, we can characterize whether the approximation is preferred for a given computational budget and loss function. Okay, so if you look at this carefully, it really shows that AMCMC algorithms can be strongly preferred if the computational budget is smaller, and often it tends to be like I start running an MCMC algorithm initially, very early on in time. I'm going to strongly prefer the approximate MCMC algorithm, but then as I've run it farther, that means I have more computational budget. I might, at some point, be preferring the exact approach. Okay, because as the budget increases, the bias is of increasing importance, and so it's worthwhile to decrease the approximation error by increasing the computational burden. Okay, so we can do this for approximations based on subsets, distribution approximations to full conditionals, and a mixture models and low-rank approximations. So I'll just kind of flash that up and be done. Okay, so let's say we did an approximation based on subsets. Well, we can replace the full data likelihood with some likelihood we call L of epsilon, which we're just taking the likelihood, and we're just taking it for those subjects in some subset V, and then we put in a stochastic approximation. And so we could run any MCMC algorithm we wanted just using this likelihood instead. And so we looked at that in the Polya gamma logistic regression case, which has been applied already in the big data context. You're choosing a different subset at each iteration It's a really easy Gibbs sampling algorithm. And so what we could show that assumption 2 holds with high probability for large subsets. And we can also, it's already been shown that the chain is uniformly ergodic, so our assumptions hold in this case. Okay? And so this sort of gives a validation for this algorithm. It also allows you some insight into the sort of choice of epsilon. So we applied it to this SUSY data set. There was a 5 million sample size, a 0.5 million test. And we cranked up the subset size between 1,000 and 4.5 million and looked at different loss functions. And so what we found is that people usually don't think about these things, and I think the theory gives you a lens which kind of sucks you into thinking about these things more, but the rate at which the loss goes to 0 with epsilon is really heavily dependent on the loss. So if I'm doing a logistic regression, and all I care about is estimating the posterior mean of a regression parameter, then I can choose really small subsets, and those will be optimal. But if I care about estimating like a credible interval, like a tail probabilities, or the width of a credible interval, then I want to choose a much bigger subset size. And of course, that's going to depend on the computational budget. Okay, so that's there. And so we also had, remember that example where we had, for WASP, where we had a mixture model for contingency tables. So we could do that same type of example, but instead of breaking up the data and throwing them on different machines, we can do a really simple and general trick, which is essentially we want to avoid sampling these latent class allocations for huge sample size. And so we just use the large sample approximation, which is adaptive. So we don't use the large sample approximation where we have small sample sizes, just where we have large amounts of information. And that avoids sampling the individual latent classes and gives you a really sizable speed up. And so again, in this case, we can show assumptions 1 to 2. In fact, our result for assumption 2 is quite a bit more general, much beyond this type of model, the broader mixture models. Okay, and so the final example we looked at was low-rank approximation to Gaussian processes. And this was really interesting because there's this huge literature on this. So there's a billion different approaches for running posterior computations in Gaussian process models. One of the more popular is known as the predictive process in the Bayesian statistics literature, and in machine learning is a subset of regressors method. It was interesting, they were sort of independently developed at different times. And so we started trying to study those, and it was really hard actually to show for those algorithms that these conditions could be satisfied. And so we actually ended up using different types of algorithms where the conditions could be satisfied, and I think those are in general often going to be better algorithms. Okay, and so we had a Gaussian process prior. We put hyperpriors on the parameters and the covariance, and we looked at a marginal MCMC sampler, which would marginalize out the Gaussian process and do updates on the remaining hyperparameters. And so we can show that assumption 1 holds under quite mild conditions, and assumption 2 is going to hold for a partial rank R eigen approximation to sigma. You can't exactly compute the partial rank R eigen approximation, but we can show we can compute something that's extremely close to it. And so this is again a case where we can show that less accurate approximations are really clearly superior in practice for a small computational budget. And it was actually stunning in this case. It was surprising that we could actually have epsilon reasonably large and have almost no fall off in performance. Okay, so I'll wrap up there. I'm out of time, but so I proposed 2 really general classes of algorithms for scalable Bayes inference, WASP and MCMC, which really isn't a new idea for us, but we're sort of putting under a framework where we can study it theoretically. And so we'd like to improve theory in the future, and our motivation is really practical. I'd like to develop really broad classes of algorithms that can be used in almost any setting. But without this sort of theory guarantees, then we don't know how much they're working in settings that we haven't studied carefully through simulations and things. It's useful to combine the algorithms, and I think it's really useful for AMCMC. It's very hard to do this type of theory, and then it's really difficult to get any handle on the constants. But I really find that by studying the theory, we actually suggested to us new classes of algorithms, like that latent class algorithm, and kind of rules out other algorithms. And so it's useful even though we don't have bounds that are exact for a given example. We don't know what alpha and epsilon are exactly. And so we had some grants, and so this work was really done by James Jandro did the work on approximate Markov chain Monte Carlo methods. He's a phenomenal student, and he'll be on the academic job market. That's him right here. The work on WASP was done mainly by Sandvesh, who's now at the University of Iowa in a tenure track position, and much of the theory contributions was made by Cheng Li, who's an ongoing postdoc. I'll stop there.